Hi, welcome back to our video series on the biological CSTR or the chemostat, and which stands for steady state chemical conditions. And yeah, on to our fourth video. In this video, we want to discuss product formation and how that affects product formation. And see how that affects our balance equations. So while the cells may be producing product, but at the end of the day, I still want to grow cells. My aim is to grow cells still. Now, how does the product formation actually affect the balance? Well, for one thing, your substrate, not all of the substrate can be used, it is being used to produce cells. It can be used to produce other chemicals which may be unwanted. So let's take that into account. So let's start again with our cell balance. So accumulation equals to in minus out plus the reaction term. Okay, the in minus out and the reaction term. So there's no accumulation and no cells going in. So the out term equals to the reaction term. So this is F into X equals to V of reactor into dx dt. So this is the net rate. Okay, so dx equals to dx by dt. So this is the net rate of cell growth. So we already found that mu net into x equals to dx dt, and well, mu g minus kd into x equals to dx dt. Right? So that's by definition. Yes, using the exponential growth kinetics, mu g minus kd. So there's no production of material. The production of material doesn't seem to affect the cell balance. So the cell balance still gives you this. This is from the cell balance. Okay. So the cell balance doesn't really change. Okay, so with the Monod kinetics, the Monod kinetics are this: Ug max S over xs plus ks. With the Monod kinetics, it doesn't change, and since the cell balance doesn't change, we can conclude that the steady state value of the substrate also kind of doesn't change. Okay, the steady state value of the substrate can still be expressed in this following manner. Okay, so this is from our cell balance and the Monod kinetics. The relation between the steady state, the steady state concentration will change due to the output of products being generated, but the relationship between the steady state concentration of substrate and of course the growth and dilution rate and all that doesn't change. So this is from cell balance plus the Monod kinetics. This is a constant. Okay, so but we still want to find what our x is, because x is the treasure. Of course, it's not the treasure, but I'm just making a pun down there. You get what I mean. So anyway, so we still have S equals to d plus kd into ks over mu g max minus d plus kd. That still remains constant. So this is the cell balance plus Monod. So we want to relate it to our substrate concentration. So let's do a substrate balance. Okay, again, accumulation equals the in minus out plus the reaction term. So this is of course 0 for steady state. So the Fs naught is in minus Fs, which is out. And of course, the VR and the ds dt due to cell growth plus VR. So I'm just using this to imply the rate. This is not accumulation, okay? This is just my own notation. So this ds dt due to product formation. Now you see that the substrate concentration actually starts to change. Okay, the substrate concentration actually starts to change because of this extra term here. This extra term. Okay, so we'll just divide everything by VR first, just to get our D, our dilution rate, which is fairly common to what we want. Okay, so what is this equals to? ds dt equals to del s del x del t. Alright, so this is 1 over y x by s into del x del t due to cell growth. Now if this is the maximum, we want, then we will just use the mu g straight. We will relate it directly to the rate of growth of cells, mu g. So this is mu g into x, y, x by s maximum. So this is ds dt. This is growth of cells, cell growth. Okay, so we'll substitute that back into our equation. Plus, or rather it's a minus now, mu g x over y yx by s maximum plus some product formation constant or product formation value variable. Okay, so this is the product formation one, this is the cell growth one. So let's just continue. How do we get this? Well, we can perform a similar trick over here. So there's one kind of analog. So we have ds dt of product formation equals to del s del p into del p del t. Okay, so this is the product formation rate. So this will be minus 1 over y p by s, and this is dp dt product. Now, of course we can perform experiments and then we can have this term called QP, which is the specific rate of production, and that is where we get this. Okay, so this is experimentally determined yp by s. Okay, and then qpx will be on the numerator. All right, so there you go. Let's substitute that back here. So we'll have 0 equals to d s naught minus s minus mu g into x over y x by s maximum minus the qp into x over y P by S. Okay. So if we make X the subject again, so we'll just shift this to the left. So we have X mu G over Y X by S maximum QP YP by S goes to D start minus S. And you'll simply have this equation. Sorry, it's getting a bit tight. QP over YP by S. And there you go. And this S, of course, remains constant. Then we can do some rearrangements here to make it look a little nicer and more presentable. But basically, that's kind of it. So oh, sorry, this should be a plus. That's a careless mistake. Yeah, so that's pretty much it. Yeah, that's pretty much it. So if we rearrange this, we will get a sort of a neater looking thing. So this will be from the cell balance here, which doesn't, okay, it's over here. It's this thing that remains constant. And that's all I have for you this video. So see you in the next video. Bye bye.